Hello. In this video, we're going to go over the input stage of your multi-stage BJT op-amp. So the first thing you're going to want to do is read the amplifier specifications, because this is what you're going to be using for your formulas. And this is the schematic for the basic differential amplifier. So the first step is a theoretical design. Start by designing the circuit theoretically and show pertinent calculations to achieve the desired specifications. So I would highly recommend that you have already done the workbook activities chapter 4 and chapter 5. Because it's going to be applied to this lab. So if you haven't done that yet, I would stop this video, go to your workbook activities, and then come back. So if you have done the workbook activities, I would go to workbook activity 5.5 because it's going to help you in this first single-ended differential amplifier with the tail resistor. So I have my basic differential amplifier, and I wanted to show you that I'm using VCC and VEE of 15. So it's different than what the lab wants. The lab recommends 10 and -10, that's the specifications. So as you're going through your workbook activity and making your design, make sure you're using the correct specifications. So the first step is you want to choose an appropriate RC value. And so to do that, I used calculations on Excel. You're going to want to take VCC, let's see, where is it? RC. Okay, you're going to want to take VCC minus half of VCC and divide that by the current, the collector current. And so when you do that, it gives you 15K. And again, this is specific for my design. So then I'll plug 15K in. So then the next value you want is the tail resistor. So the tail resistor uses the full current from both branches, and our lab specifications say that the collector current is 0.5 milliamps. So if the collector current is 0.5 milliamps for this branch and 0.5 milliamps for this branch, they add together at that node and turn into 1 milliamp. So we need to figure out how to get 1 milliamp here. Well, using Ohm's law, we can just take VEE divided by 1 milliamp, which will give us 15K. Okay, so now the third step is to choose the emitter resistor to get a gain of 25. So going to my Excel file, this is the formula for gain, and I want you to observe that this uses RC in the numerator. So that means that we would not have the load connected. If you want the load connected, then that value should be RC in parallel with RL over 2 times R prime E plus RE. So just for me to double check that, it looks like, yep, I have the load resistor in there, so we're good. RC in parallel with RL. And so doing that calculation, usually when I have something in Excel like this, it's really easy to just kind of do the different iterations. So you could start out low, see what your gain is. 43 is too high. You could do 1,000. Now we're too low, right? So then you can just split the difference. Now we're at 11.9 until you dial it in. That's one method of doing it. So 210 ohm resistance in the emitter resistor gives us 25.1, gain of 25.1. Again, you can manipulate this formula to get RE, but when you build it all on Excel, it makes it pretty easy to just kind of plug in different numbers and get the value you want. If you plan on building this circuit, 210 ohm resistor is not a common value, so you might want to go with 220 or 200. But just for theoretical and simulated purposes, I'm just going to go with 210. Okay, so 210. And I'm going to run this. And we're going to measure the peak-to-peak value. So I am inputting a 0.2 volt signal, and I'm getting 4.76 volts out, which is about 23.8 gain, a gain of 23.8. So we're in the ballpark range. Okay, so if you want your simulations to be exactly 25, you know that you're going to have to change the emitter resistor. But I would observe that and note that in your presentation, your lab report, that there was slight differences between the theoretical and the simulated. And if you build it, there's going to be differences. So that is something that you're really going to want to pay attention to, the emitter resistors. Okay, so now going back to the lab, we got the RE for the gain. You're going to want to calculate the input resistance and make sure it's over 50K. The common mode rejection ratio, to perform that in simulation, what you're going to want to do is just apply this Vin positive to both signals. And then you would run it, and you would see what the peak-to-peak value is, and then that's your common mode gain. To do it theoretically, you would just calculate it. And again, if you're using a load resistor, you're going to want to make sure you're using the appropriate formula. So now, you want to do all the CAD simulations for this, which I go over all of these in the Lab 1 videos. So if you need help with your transient analysis, or like here's a tip, you may want to avoid taking measurements in the first few cycles to allow the circuit to reach steady state. I go over that in Lab 1, so you might have to refer to Lab 1 for some of these CAD simulations. And the maximum output swing, that's just simply increasing the input to see clipping on the output. And to go to the specifications, the V out max should be greater than or equal to plus or minus 2 volts. So I go over that in lab 1. Okay, now we're at step 3, circuit improvements. So you're going to want to add a current mirror and an active load to improve the circuit. So to do that, I would recommend referring to chapter 4 in your workbook activities, because chapter 4 goes over all of the current mirror applications, and there's a lot of different current mirrors you can go with, but the one that I'm going to show is the cascode current mirror, and then we're just doing a simple active load. And again, I'm only using I'm using 15 volts for VCC and VEE. So when you do your design, make sure you're sticking with plus and minus 10 volts. Okay, so what's different in the calculations? Well, we can see in the schematic that there's no RC anymore. So looking at a few of the formulas that you need, these are not all the formulas you need for this lab, but these are just a few that I wanted to point out. Your differential gain is now the output resistance of the transistor, where before it was the collector resistance, or the collector resistance in parallel with the load. So if you are connecting this circuit to a load, it would be the output resistance of the transistors in parallel with the output resistance of the transistor in parallel with RL. And workbook activity 4.8 goes over that for calculating the gain of the circuit. Another issue is the common mode rejection ratio is going to be using the output resistance of the transistor. So you could see how this is going to change our calculations and our circuit slightly. So that portion has to do with the active load. So now we're looking at, okay, well, what about our tail resistor? Now we have this current mirror. How do we calculate our tail resistor? Well, before, we would calculate it by simply using VEE divided by the total current. Well, now we have this voltage drop between the base and VEE, and these two transistors, the base and the emitter, and then the base and the emitter, which is connected to VEE. So that's going to change the formula that you want to use. So you're going to want to include that. VEE minus 2 times VBE divided by the reference current will give you the appropriate value of your reference resistor. So your VBE, if you're making theoretical calculations, is 0.7, but in simulation you can measure that. So I'm going to run this and just see, okay, between this point and the emitter, and then the base and the emitter, what is the difference? So we have 15 volts and 15 volts and 13.69 volts. That's how I come up with a VBE of 0.655. So if you want your reference to be a little bit more accurate for the simulated version, or for the actual, if you were building the circuit, you would want to use the actual voltage drop. So doing the calculation, and let's see, doing the calculation for RF, I get 13.69K ohm. So then I would just do 13.69K. And then now we need to figure out what the RE value should be to get a gain of 25. So you could use this formula, but also include the load resistor. So our little RO in parallel with little RO in parallel with RL. And that should get you into a ballpark range. Again, if it's not extremely accurate, just know that you can adjust that emitter resistor to get a gain of 25. And take a look at, not having a load versus having a load, and experiment with different load values. So again, the minimum load should be 100 kilo ohms. So you want this amplifier to have a gain of 25 at 100 kilo ohms. So, and then you're going to want to look at the current mirror and the active load and find like key reasons why you would include those. So the common mode rejection ratio and gain. So I hope this helps with this lab, and next video we're going to go over the multi-stage op amp, which we are going to use this schematic that is provided. Thank you.